announcement. There's a conference photo at 3:10 p.m. And we'll meet in the hall out here at 3:10 for the next break. It's the main break in the afternoon. Okay. So I'm happy to have Tyler Jarvis here to discuss W curves and groups.
So actually maybe it's a little misleading because I want to discuss W curve. I'll just discuss the consequences of the theory. So, what I'm going to describe is joint work with Young and Rwan and Wei-Jun Fan and a large number of other people as well. And I'm going to try to describe a sort of orbifold Landau-Ginzburg A model, and which satisfies some kind of Landau-Ginzburg mirror symmetry, and also seems to be the right thing for Calabi-Yau Landau-Ginzburg correspondence. So it seems like the right thing. So what I want to do is, well, I'm going to focus on Landau-Ginzburg to Landau-Ginzburg correspondence. And what I want to do is start with a singularity. By singularity, I just mean a polynomial W in n variables, quasi-homogeneous. And non-degenerate, by which I mean that it has an isolated singularity at the origin, or if you want to think of it as defining a hypersurface in weighted projective space, then it would be a non-singular hypersurface in weighted projective space. One additional condition that maybe the weights are uniquely determined. So here's some examples. I'm going to be talking about these several times. The AN singularity is just x to some power. E6, 7, and 8, the exceptional singularities. So here are the weights of each of these that make the polynomial have total degree 1. Dn is a little bit more interesting than the others, I think. So the weights aren't, they're still straightforward to compute, and P8 is another one that we'll talk about briefly. So the thing about these weights is that there's a special element in the group of automorphisms of these things. So, very nice, thank you, John. So if I want to look at the group of automorphisms of these things, I only want to allow diagonal automorphisms. So this will be only things in C star to the n that fix them. So W alpha 1, x1. So that's the group, that's what I want to consider the group of automorphisms of this thing. I'm not going to allow non-diagonal symmetries. But there's a special element in Gmax, which I'll call J, which is what? It's just the exponential of the gradient of the degree. So it'll be exponential of 2 pi Q1 and so on. And it's easy to see that lies in Gmax, and it will turn out that sort of the fundamental, an essential element that in order for us to do this, we're going to do this orbifold theory, and which means you choose not only a singularity but a group, a subgroup of Gmax, but the requirement will always be that J be an element of Gmax. So that's what, when I say an admissible subgroup, I'll mean a group which contains, a subgroup of Gmax which contains J. So here's the theorem, or a compilation of many theorems all put together into one here. But essentially, for each non-degenerate W, for each non-degenerate singularity, and each admissible group, a subgroup of Gmax containing J, first is a moduli space of W curves. So Orbi curves with some additional structure, which I will not describe today. If you want to hear a longer talk, then I can do that some other time, I guess. So it's finite over the moduli space of stable curves with fixed number of points. There's a state space, which looks like your usual orbifold state space, that is summing over various, so for each W and G, you sum over the elements of G, and you get a sector for each G, and it pairing that matches the gamma sector with the gamma inverse sector, and a virtual cycle, which behaves a lot like the virtual fundamental cycle of Gromov-Witten theory. It satisfies similar axioms as well as some additional axioms that make it possible to compute, which is why the theory is interesting. Now, what you can do is take this virtual cycle, which lives up here, and push it down to the moduli space of curves, and quantitative dualize and so forth. That gives you a collection of cohomology classes on the moduli space of curves, which together with the state space and with this pairing give you a cohomological field theory. Which means essentially that they behave well under restriction to the boundary. So under the standard gluing operations that you get in the moduli space of curves, these things pull back nicely along those gluing operations. So associated in cohomological field theory, you get some natural things that arise, right? So if genus is 0 and you only look at 3 mark points, I guess what I've called n here, I called k before. I apologize for that. Anyway. Genus 0, 3 mark points, you get a Frobenius algebra. So if you look at your state space and you use the 3-point correlators from the cohomological field theory to give you the structure constants of multiplication, that gives you a Frobenius algebra on that state space. And you can do better if you look if you look at the entire genus 0 theory, then of course you get a Frobenius manifold. And if you look at the entire theory, you can assemble all of the correlators together in the standard way. You get a potential. A higher genus potential function. So, of course, they're similar. So this is all what I would consider the A side of this Landau-Ginzburg model. And now, on the B side, we also have similar construction. So the Landau-Ginzburg B model, chiral ring, or the Milnor ring, is a Frobenius algebra. And associated to each singularity, you can also construct the cyto-Frobenius manifold structure, which turns out to be semi-simple for each one of these singularities. And then Giventhal has described a way that you can start with a semi-simple Frobenius manifold and construct a higher genus potential in a formal way, so not based on a cohomological field theory, but so we've got these things that are sort of similar to the construction that we had on the A side. And in some cases, there is also an integral hierarchy.
You don't have
what?
Sorry? You don't have a group here.
Right.
Just the only
That's right. This is the B. On the B side, there's no group, right? Yet. I'll talk more about groups in a minute. But so on the A side, in each case, I had a group. So it was an orbifolded model. This is a non-orbifolded model. Right, but on this B side, in addition to these other constructions, sometimes there's an integral hierarchy, and when all is well in the world, then this potential can be a tau function solution for the integral hierarchy. So that's sort of the big picture. And so so Witten made some conjectures a long time ago. 20 years ago, he made a conjecture about what happens in the AN case. Long before this theory even really existed, sort of sketched what ought to be true, and conjectured essentially that the A model, so I should say that the AN case corresponds to what we call the R spin or higher spin theory, and it's easy to verify that the A model, the AN case matches the Milnor ring. It would give us the 0 and 3 mark points. For the Frobenius manifold, it's substantially harder, and so we did that together with Takeshi Kimura and Arkady Weintraub about 10 years ago, and then Whitey Lee showed how to make that match the Giventhal potential in genus 1 and 2 a while ago, and more recently Faber, Jarvis, and Zonkin showed how to do this in general. And Giventhal had already showed that his potential in the AN case satisfied the corresponding hierarchy. So that completed the proof of the Witten conjecture in the AN case. Well, what about the others? So we have so Witten extended his conjecture to all simple singularities, so A, D, and E. And so in the E case, it's very easy again to check. Well, not easy, but one can check. And so with Wijun and Youngbin, we proved that the Witten conjecture is satisfied for all of these cases as well. So again, you'll notice in this case that Gmax is the only group that contains J. So for all of these cases, there's only one group to choose from. There's only one admissible group. But in the Dn case, when n is even, it's the first time that you have two choices of group. So J actually has index 2 in Gmax, and so that you've got these two groups. But in the case the group is J, again, you do have exactly Dn on the B side matching Dn on the A side. So what's strange, though, is that now if you go the next step to Dn with Gmax, you don't get Dn. So Witten conjectured that you should have Dn here as well, but in fact you get A2n minus 3, which is sort of a surprise. So the secret here, I guess, is Mark Kravitz noticed that A2n minus 3 is really the Berglund-Hübsch dual, where there is a way of describing A2n minus 3 as the Berglund-Hübsch dual of Dn. So let me explain what that is. So Berglund-Hübsch duality sort of fits into, well, it is a nice way of describing mirror duals in many cases, but I think it's sort of been forgotten for a while. But so it's very simple. Right? If I start with the singularity W, let's look at Dn in particular. So you take your singularity, your polynomial, and you build the matrix of exponents. So in the first case here, so this is the n minus 1 is that exponent. I've got no y on that term. I've got a 1 here and a y squared. I build that matrix, and I just take the transpose of that same matrix. Very simple. And that gives me a new singularity, x to the n minus 1y plus y squared. And so if this is Dn, I'm going to call this Dn transpose. And what Mark Kravitz noticed is that as a singularity, this is isomorphic to the An singularity. So in particular, all of the B model constructions, the Milner ring, the Cyclotronius manifold, and the Kubitschek potential, all match Dn transpose. So even though it looks like it didn't fit in the picture, in the Witt's picture, something more interesting is going on. So now the question to ask yourself is, well, if the A side matches up with the Berglund-Hübsch dual on this side, why do these not match up with their dual? And the answer is, in fact, they do. So if you think about An, the An singularity is self-dual, right? And x dn plus 1, I mean, it's that matrix, right? So it transposes itself, so it's self-dual. Similarly, E6, 7, and 8, so all of these, E6, 7, and 8 are all self-dual. So this picture now looks almost like the correct picture is everything transposed rather than untransposed, as we thought before. And so then the obvious other question to ask is, what happens if I put Dn transpose in here? Oh, I should say, it's not so obvious a question, right? Because if Dn transpose is isomorphic to the singularity to An, why would I think they're different? Well, it turns out that our construction is actually is fine enough to distinguish between different singularities. I mean, the same singularity with different ways of expressing it as a quasi-homogeneous polynomial. So it's a more refined invariant than just isomorphism class of singularities. So Dn transpose is actually not isomorphic in our theory to An, but on the B side can't distinguish between those. So on the B side, these are isomorphic. On the A side, they're not. And if I take the Dn transpose and compute it there, and again, there's only one choice of group here, I in fact get Dn, which is Dn transpose transpose. So it fits all nicely into the picture, except that Dn itself, this one case, Dn with the group J does not fit into the picture because Dn is not self-dual. But the one thing that you notice is that all of these are Gmax, and this is the one case when Gmax is not equal to J. So So how does that get resolved? Well, the idea is there should be some way of dualizing the group J to get a new group of order V2. So in addition to taking this diagonal transpose, we need also now to orbifold on the B side. And on the B side, so we have W going to W transpose. G turns out goes to a group called G transpose, which has the property that the order of G is equal to the index of the original G in G max. So where the index here is 2, the order of G transpose is 2. And so then the conjecture is, before I say the conjecture, say what is an orbifolded Milnor ring? Well, Interrogator Vafa gave a sketch of an outline of what the orbifolded Milnor ring should be as a vector space, and Kaufman and Kravitz described a way of putting a multiplication on that orbifolded Milnor ring. So there is an actual, on the B side, there is an actual candidate orbifolded Milnor ring here. And so the conjecture is that that the A model, our theory, JRW, should W mod G as an orbifold theory should be isomorphic to the, on the B side, W transpose mod G transpose. So, and this fits into that picture. What's not clear, well, and so at the Milnor ring level, that fits. At the Frobenius manifold level, it's not clear how to orbifold the Frobenius manifold in general. In the specific case of Dn transpose mod V2, I think we have a way of describing that which is compatible with this, so that these are isomorphic. And so Takashi and I have some ideas about how to orbifold in general. And then the Gibbons-Hall potential, it's not clear how we construct the Gibbons-Hall potential from this. But in this specific case, since you have a regular Frobenius manifold that's semi-simple, then you can go to the Gibbons-Hall potential as well. So let's look at now a more general picture. So here's a couple other interesting results. But let me focus first on the bottom part of this. So for an arbitrary invertible singularity, so you'll notice this trick of going from W to W transpose only makes sense if the number of monomials is the same as the number of variables in your polynomial. I mean, if your matrix is square, and otherwise, what would the transpose be? But if I have an invertible polynomial and I look at the group G max, then Kravitz, Pedro Acosta, and Yifeng Shen showed how to have proved that the A model construction matches the B model construction at the Milnor ring level. And more recently, my students Amanda Francis and Drew Johnson and I showed that this works for general G, at least for most invertible W. And then there are a few cases that we're still working out. But that looks like that all works. So the conjecture is true at the Milnor ring level. At the Frobenius manifold level, that's still open in general, but seems like it is going to work. And of course here, that even needs to be constructed. In the case that the Frobenius manifold is semi-simple, then we hope that we could also construct a Gibbons-Hall potential to match it. I should mention also that Kravitz and Yifeng Shen have looked at the additional cases, these elliptic curve singularities, P8, X9, and J10 with G max, and have showed that the whole construction is essentially satisfied. There's some details at the potential level. Is that correct, or is it all now?
No, it's okay. It's all. But there's no integral hierarchy.
Right. I thought there was an integral hierarchy that was a candidate. No. Okay. All right. All right. So to cross that off. I'm sorry. So that's the basic picture that these that it looks like it's working in all cases that are of interest, but there's a big question about what's happening at the Frobenius manifold level and beyond to how to construct those. So, thank you.
Questions? I completely blanked out during the exposition of the actual equation for the singularities. These are all surface singularities?
No, but
No, not necessarily surface singularity.
so they're not necessarily in A2.
No, right. So in fact, these in particular are in three variables. So projected weighted projected 2 space, whereas the others were in weighted projected 1 space. But
So 3 by 3 matrices that get
n by n matrices are perfectly fine. And and there are some nice properties about if I take sums of singularities that have distinct variables, then this gives me a tensor product of theories. So I can make things arbitrarily large and understand them already with our simpler pieces.
Have you made any other attempts using other mirror constructions like Patrick's?
No, I haven't. I mean, talked with Patrick briefly about that, but I haven't pursued that anymore. And I know, so Barsov has a way of thinking about these, of fitting the variant picture into the Borisov criteria duality now. I mean, originally that wasn't the case, but I think more recently he's got that. So on the B side, his construction seems to match. On the A side, it's not at all clear that his A model matches the FGRWA model. So I guess that would, if you want to prove these theorems, another way of doing it, at least at the Milnor ring level, is to match what Lynn has.